Oops. Okay, so usually this class is preceded by some course like Signals and Systems or DSP. So in those classes, we spent a lot of time on the Fourier transform. Okay. And even though we're going to spend this week talking about Fourier transform stuff, and it is important for image processing, we're not going to, belabor the point like we did in Signals and Systems, right? So we'll talk about it, and it's an important concept, and it will come back at us when we talk about things like, the radon transform and so on in next month after exam 1 or exam 2. But I just want to talk about how it works in image processing. And so the first thing you learned when you were talking about a continuous time course was basically the continuous time Fourier transform. Right? So that would basically say that if I had a input signal x of t, the output signal was given by this. So here x of t was a continuous valued input. I guess I can make this a little bit bigger. X of t was a continuous valued input signal. X of omega was a continued valued frequency signal, right? Then, if you took DSP, we talked about something called the discrete time Fourier transform. And that was more appropriate for digital signals because we assumed from the get-go that we only had discrete samples of a signal. And so the integral turned into a sum. And so instead of integrating over a whole bunch of continuous values here, we summed over an infinite number of discrete values. And here, this omega was continuous in the range minus infinity to infinity. This omega basically wrapped around in the range 0 to 2 pi. Okay. And then finally, we talked about what was called the discrete Fourier transform. And that was applicable to signals where instead of having an infinite number of time samples, we instead had a finite number that we were assuming wrapped around periodically. And so then we defined this guy here, where n was the discrete period of the signal, and consequently what came out was a discrete set of DFT coefficients. So here, the difference between this and this is that this x of n was infinite length, this x of n is finite length. And we showed, for example, that these x of k's would actually correspond to sampling x of omega at evenly spaced intervals. So I'm not going to teach this lecture of DSP all over again. You can go back and take a look at the video on YouTube where I go through the whole connection thing, right? And we spent a lot of time talking about the relationships between these Fourier transforms and how filtering signals kind of work both in the time domain and in the frequency domain, right? So we talked, for example, about how you could use low-pass filters to remove static-y sounding noise from a signal. We talked about how multiplication in the frequency domain corresponds to convolution in the time domain. That's why it was so easy to apply linear systems in the frequency domain, because all we had to do was take the Fourier transform of both the filter and the input, multiply them together, and take inverse Fourier transform. So all that holds together for image processing as well, right? And so we have to think about what is the natural analog to the Fourier transform for a digital image, right? So I'm not going to go through the whole hierarchy of Fourier transforms. I'm going to start from the point where we say, okay, this is a course on digital image processing, right? Digital is in the title, so we don't care about continuous time stuff. And secondly, we know that an image by its very nature is a finite, x and finite y, right? So we're already in the world of this, right? So we need to think about how to make this into a 2D version. And it's pretty easy, so we're just going to follow our nose, and we're going to define the 2D discrete Fourier transform. Okay, and so I'm just going to kind of keep my old 1D Fourier transform here just for reference. So it's basically the most natural thing. So I'm going to say And actually, just to avoid confusion with x and y, I'm going to say that, let's call f the output image, and what we're going to do is we're going to sum over the x values and the y values of the input image. And we have to take these to this exponential. So basically, it's just like a bigger, messier version of the 1D transform. So this is the input image, which I assume is m by n. And that means x is ranging from 0 to n, y is ranging from 0 to m. Here, the output image, again, is assumed to be m by n. So u goes from 0 to n minus 1, and v goes from 0 to m minus 1. Okay? And just in the same way that there's a Fourier transform, there's also an inverse transform, which I'm going to write down just very simply. It looks almost exactly the same, except now we're going to sum over the u's and the v's, and we're going to sum over the values of the 2D DFT. And instead of having a negative sign, I have a positive sign. So again, this is basically just carrying over exactly what we knew from the 1D case over to the 2D case. Okay. And in fact, sometimes, let's just say that if you have m equals n, which means the image is square, then this thing becomes 1 over n squared. And just as a comment, sometimes you may see, instead of having the 1 over n squared here and nothing here, you may see the formula like, the Fourier transform has a 1 over n, and the inverse Fourier transform also has a 1 over n. The idea is that you kind of make these guys look as similar to each other as possible by moving one factor 1 over n over. So just be a little bit careful when you look at and read a paper or you have some code that influence the DFT. You want to make sure you understand where that factor of 1 over n lands. Okay. Okay. And so the nice thing about this formula is that because of the way this exponential decouples, I can actually write it like 2 one-dimensional DFTs, right? So what I'm going to do is I'm going to take this formula and I'm going to make it a little bit easier by writing it in a slightly different way. So here, I'm going to say another way of writing this is sum over the x's, and I'm in parentheses here, sum over the y's, and then I'm going to just take the exponential part in y, and then I'm going to take the exponential part in x, like this. So basically, the idea here is that this is like, one-dimensional DFTs along the y direction, so this would be like along the columns, and then these would be like one-dimensional DFTs along the rows. So basically what this comes down to is the 2D DFT is separable. We don't need to write separable. We don't have to write a whole different 2D DFT function. We can just use the 1D DFT function that we already have and rapidly take the DFT by taking DFTs along the rows, DFTs along the columns. And actually, for those of you that took my DSP class, you remember that we actually came up with something that would look like very similar to this when we were talking about efficient ways of doing the DFT, right? We talked about if we wanted to do the Cooley-Tukey or the Good-Thomas DFT, we'd rearrange the one-dimensional signal into this kind of array, and we do DFTs along the rows, DFTs along the columns. So it's kind of like related to that, okay? So again, you should never hopefully have to write this yourself in the real world. So Matlab has a function called FFT2 that is a fast way of computing the DFT. So remember from DSP, FFT stands for fast Fourier transform. So basically it's accomplishing this computation using a bunch of quick tricks to make the processing computationally efficient, right? And we spent a couple lectures in DSP talking about some of those tricks, right? Things like radix 2 algorithms and Cooley-Tukey for lengths that can be prime factored and stuff like that. So again, I'm not going to talk about that too much here. What I really want to focus on here is the impact on image processing. Okay, so let me pause and ask first. Any questions about this? Again, if you want to go back and review 1D FFTs, you know, I can link to my DSP lectures from last semester if you want to kind of brush up on that. But the basic idea is that, you know, as with 1D DFTs, you know, the 2D DFT is like a decomposition of an image into complex exponentials, which are a different way of thinking about sines and cosines. Right? Because this critical guy, e to the j 2 pi ux over n, for example, right? We know from Euler's formula this is the same as cosine of this minus sine of this. So cosines and sines, if I were to expand all that stuff out into the real part and the imaginary part, would figure prominently in these equations, right? And so kind of what it means is, just to be really sketchy, that, you know, I have some input signal, and here I'm kind of drawing it like a continuous line because it's easier to draw that way. So if this is my input signal x, really what I'm doing is I'm saying I have the first DFT coefficient corresponds to the weight on a constant term, dc. Then I have some coefficients that sit on sines and cosines that vary slowly, and then I have some coefficients on sines and cosines that vary twice as fast, and so on. Right? So that's the kind of Fourier intuition. And a good way to think about this, and we're going to think about this kind of throughout this lecture and also the one on next Monday, is it's kind of saying that we're taking the original signal or the original image and we're writing it in terms of a different set of basis functions, right? So here we're representing the signal in terms of what is the value at every pixel, and that's kind of like the time domain or the spatial domain basis. Whereas here we're representing the signal in terms of the same number of values, but those values now represent how much contribution is there from each of these sinusoids, right? And so these guys here kind of become the new basis functions for the image. So it's kind of like saying how much of this sinusoidal-like image is in my original image. And if I add up those m times m numbers times those basis images, I get back the original image, right? So it's just a different way of thinking about representing the original image. And one of the most valuable reasons for doing that, as we're going to talk about after the exam, is for things like image compression, right? We're going to talk about how transforming the image into a certain better basis will help us throw away perceptually insignificant parts of the image that allow us to really reduce the number of bits required to describe that image. So again, we're going to talk about that in a little bit. But let me just show you, right? So let's think about what are the basis functions corresponding to the DFT, okay? And of course, bad news is that the basis functions are complex, right? So to get the coefficient, for example, to get one of these coefficients, I'm multiplying what used to be a real valued thing by some complex numbers, right? And the result is going to be that every one of these guys here is going to naturally be a complex number. Now, there are some symmetries to those numbers, and I'm not going to spend any time talking about, well, maybe a little bit of time. I'm going to talk about a lot of the various properties. It turns out that when the image is real, and our images are always real, you're going to have some sort of a symmetry between certain coefficients in the Fourier transform, right? Which means that you don't actually need all those complex numbers. You can just represent, half of them, and you'll be okay. I think it's easier to visualize with Matlab what those basis functions are. So let me go over to a little function I wrote. So what I did was basically wrote a little function called basis function. And all I'm going to do is I'm going to say, show me, if you ask for the mn Fourier coefficient, show me the real valued part of that. So it's going to basically look like some sort of a cosine of an image. And so if I look at the 0, 0 basis function, that's just going to be a constant image, right? That's kind of like the equivalent of a DC term for images, right? So it's kind of like saying, how much of this flat image do I have? And if I ask for the first basis image, 1 in one direction and 0 in the other direction, I get a kind of a sinusoidal image, but just in, for example, here I've got constant columns and a sinusoid in terms of the rows, right? And if I were to crank up the number here, I would get more things. So again, you have to think about what you're seeing here. So again, here, black is being scaled to the lowest value, which in this case is going to be -1, and white is scaled to the highest value, which is going to be +1. So this is like an image that's oscillating between +1 and -1, and you can kind of imagine what the, if I were to make a surface of this, you would see, actually I don't see why I couldn't do that. So let's, for example, take this guy here, and if I were to just say surf of B, and turn off the edges, right? So this would be what would look like, this would be what the image would look like if I were to perceive it as a surface, right? And again, I can keep on cranking up the, the values until I get these very fine wiggly cosines, and at some point, I forget how big my image is, 256 by 256. So at some point, as I crank up to the highest frequency, I basically get what looks like an alternating pattern of black and white lines, right? That's like the highest frequency thing that you can get in the image world. And kind of conversely, if I were to start doing this in the other side, I would get the sines and cosines going the other way, right? So these are the basis functions here. But also I have these kind of coupled basis functions. So for example, if I have a basis function that is, the first x and the first y, I get these kind of stripy diagonal lines. And depending on the ratio, so depending on, if I do this, I get finer diagonal stripes. If I have a slightly different ratio, I get diagonal stripes that are at different angles, right? So I can kind of make the angles of these stripes different depending on, the relative ratio. And if I were to look at this guy, for example, I would see that the Fourier transform here is kind of like, a sinusoid that wiggles in both x and y directions. And so kind of from this angle, it's wiggling 5 times, and from this angle, it's kind of hard to tell it's wiggling, 2 times, right? So that's what you get when you multiply these basis functions together. And of course, it's a little bit more hard to visualize that this is actually just the real part of a complex function. But that's the basic idea, is that, again, I'm decomposing an image into how much it wiggles in different directions, okay? So, and just like in one dimension, so let me pause and ask for a second. So questions about the, just the way these basis functions look. And in some sense, I think it's easier to visualize this stuff for image processing than it is for signal processing almost, because you can really get an intuitive sense of the things that are adding up to make your image, okay? And again, you can kind of see, and we're just kind of a preview of the next lecture, is that, high frequency stuff, right? So high frequency basis functions, they start to look basically just like noise. I mean, it's kind of structured, but it's still noisy, right? And so we're going to start to understand, okay, this is what things look like in the low frequency domain. Low frequency parts of the image are usually nice, big, flat, slowly varying regions, and high frequency parts of the image are edgy, noisy parts of the image. And so just like if we wanted to remove, staticky noise from an audio signal, we would low pass filter it. In the same way, if we had this kind of crappy, noise added to an image, we would low pass filter the image in 2 dimensions to get back a slightly better original image. We're going to talk about that more next time in terms of actually doing frequency domain filtering of images. Okay. And so actually, while we're here, let's look at the Fourier transforms with some images. And so All right, so here we go. So here are some nice Hawaii images. So this is a pretty normal, well, actually this is maybe not as normal as I want. So let's talk about this image first. Get off these warnings. I know what I'm doing. Okay. So here is a, nice looking regular image that you take on your vacation, right? So what do we get when we take the Fourier transform of it? So here, first we can do it directly, right? So I can just say, let's look at the FFT2 of this image, okay? Now, again, if I look at this, it's the same size as the original image, but if I think about, the first few elements of it, I can see that it's got complex numbers in it, right? So I can't really directly visualize this thing. What I could do instead is I could, for example, look at the absolute value of this image. And of course, since it's got weird numbers, I need to scale it so that, the lowest thing is black and the highest thing is white. So if I look at that, not so exciting, right? So one reason for that, and let me make sure I'm not crazy. Yeah. So one reason for that is that, these values can get very small, right? So if I were to look at the, what would be a good way to do this? If I were to look at the histogram of the values of the Fourier transform, what I would see would be, a lot of very, very small values and some very big values. And if I were to show that histogram in the log scale, I could see that, here, let's see, having a hard time remembering how I'm trying to determine this. So here's the histogram of the output. Oh yeah, so this is, right. So basically, there's a range of values. If I view things in the log scale, things are a little bit more evenly dispersed. And if I look at the image of the log scale, like this, again, this is not like a super exciting image. And part of the reason it's confusing to look at is that, let's think about the way this works. So the upper left-hand corner is DC, right? That's the 0, 0 element of the Fourier transform. And that, again, if we look at my formula, so here, let's look back at this formula. So what is f of 0, 0? Well, that means I plug in u equals 0 here and v equals 0 here. That means both these guys turn into 1. And what I get is basically the sum of all the pixel intensities, right? So that's going to be some really large number. And that's another reason why we want to show things in the log scale, is that that huge number swamps the magnitudes of all the other values in the Fourier transform. And so if I go back to my Matlab image, I can see that there's that really big number in the corner. And in fact, if I were to ask myself, what is that number, I could say, out the first value is some massive number, right? Which is the same as all the values of the image, right? So I need to kind of scale that down to be able to see something useful. The other thing that's a little bit confusing is that, we have this periodicity in the two-dimensional Fourier transform, right? And that's what makes it a little bit weird to visualize, is that here, all this stuff up here is low frequency, and as I move this way, I move into high frequency. But then, just like in the one-dimensional DFT, I have this kind of wraparound problem where kind of at pi, right? So where the 1D DFT is defined between 0 and 2 pi, right? But 0 and 2 pi are the same point on the unit circle, which means that as I go around from 0, I start to go around the circle. By the time I get to pi, that's the highest frequency I can get. Then I start going back around to 2 pi, and I start to go through low frequencies again. So that means that actually the highest frequency point in this image is right in the middle, right? Because as I go further this way, I'm going low frequency in one direction. As I go further this way, I'm going low frequency in the other direction. And so visualizing the FFT like this is a little bit confusing. So one thing that Matlab lets you do, I mean, of course you can do it yourself, is it makes more sense to shift the FFT so the DC value is in the middle. So if I do that, now I get something that's a little bit more easy to interpret in the sense that there's a lot of frequency content in the middle near low frequencies, and as I go further out to the edges, I have less frequency content where there are high frequencies. Okay? So again, the way I think about this is that there are going to be, high frequencies correspond to edges in the image. So if I have a really edgy image, I should have lots of high frequency. And if I have a really low, smoothly varying image, I should have low frequencies, right? And so here, I kind of see this general phenomenon, and you're not going to learn a lot from this image, just that most of the bright parts are towards the middle, right? That's the take-home message from this. Now, there are some pretty strong white bars here, and I'm going to talk about that in just a second. But one of the reasons that there are white bars is that there is this implicit assumption that the image wraps around the edges, right? So remember that, and I'm going to talk about this a little bit on paper in a minute, but kind of a critical idea is that for the 1D DFT, right, it's not like I have just, n values and I stop, right? The assumption behind the 1D DFT is that things are, periodically repeating. So outside this interval, I get the same guys again. And so the way I think about the 1D DFT is actually that I have n unique values, but those n things repeat across the time domain. In the same way, those n things repeat across the frequency domain, right? That's why I only have this kind of sampled 0 to 2 pi window, and everything else outside of that is just something that I saw before, right? So how does that work in image space? Well, again, the assumption in image space then is that when I take the 2D DFT, it's like I take the images that I've got and I tile them in the time domain. And so if this is my original image, that means that Matlab is thinking, hey, this pixel has these two neighbors here. This pixel on the edge of the image has this neighbor here and this neighbor here from the right-hand side of the image, right? And so the fact that you've got these images stacked together means that you may be introducing some edges across the image boundary that you aren't thinking about. And so a good way to think about that is, what if I were to take my original image and shift it to see what the middle of those tiled images would look like, right? So if I do this, here's my waterfall image. You can see that actually there's a lot of edges in the horizontal and vertical directions coming from the fact that there are discontinuities across the boundaries of the image, right? If I wanted there to be no discontinuities, as I went across the right-hand side of the image, I'd have to overlap and smoothly continue on to the left-hand side. Most digital images don't look like that, right? So that means that there are, like here, there's an incredibly strong dark to light boundary that is going to get picked up in the Fourier transform saying, hey, there are a lot of edges in this direction, right? In real life, there really aren't. Here's an example of something that may work a little bit better, right? So let's take a look at another image. So here is an image of, I guess first let me show you the original. Okay. Right, so here's an image that I took looking into a volcano at night, right? So things to observe. So first of all, there's a lot less sharp edges going on in this image overall. There is this one, this is like the guardrail so you don't dive into the volcano. But if I were to look at the tiling of that image, hopefully it would be a little bit less, well, I guess fftshift doesn't really know what to do with this. So let's make it a grayscale image. Right, so here, actually the boundaries between things are a little bit less, in fact, certainly there's no real obvious horizontal boundary here because it's dark at both the top and the bottom. there's a little bit of an edge boundary here, and so if I were to look at the, FFT of this. So again, just a reminder that when I do this, I'm concatenating a bunch of things, right? I'm looking at the absolute value because they're complex numbers. I'm looking at the log because the DC value is so big. I'm looking at the FFT shift to put the DC value in the middle, okay? And so if I do that, I get this thing. And here you can see, well, I'm sure that you're convinced. I was hoping it would be more convincing. But here you can see that, let's just take a look at this for a second. So I'm going to try and compare a couple things. So instead of naming everything the same, so let me call, oh, so let me show you one thing. So, oh yeah, that's a good point. Good point. Interesting. So actually, let's interpret this. So here, it looks like, again, the scaling makes it a little bit more confusing. So let's actually try and compare these two FFTs. So my first image was the valley. Okay. So let's call that M1. And my next image was the volcano. And let's call that, oh, god damn it. All right, let's do this again. Call this M2. Call this out 2. Okay, so let's look at the, and let's just make a couple of quick substitutions. So let's say that this is going to be the log of the absolute value of out 1. And this guy. And let's look at the max of these guys. Okay, so I'm going to try and scale these guys to both be on the same scale. So let's say we go up to 18.5. And now what I'm going to do is I'm going to show the FFT shift of 01, and I'm going to scale it to make the maximum value of this. Now I'm going to do this. I didn't actually try this at home, so I'm not sure how convincing this is going to be, but this is. Okay, so on the left is the valley image FFT, and on the right is the volcano image FFT. And so one thing to see here is on the same scale, the volcano image FFT has a lot fewer high frequencies, which is what we expected, right? So the valley had, beach and trees and edge contrast in the foliage. The volcano image is basically a dark image with some very low frequency, clouds of steam coming out of the volcano, right? And so I can see, number one, that there's definitely a lot less, low frequency stuff. What I was hoping to see, which I'm not sure is like totally convincing, although I think it's okay, is that if I were to make a guess, I would think that the, let's try and zoom in on the middle here. I would think that the middle region here, I was hoping that I would see that there would be fewer, like that the straight lines here that cross the middle of the image would be a little bit darker here than here because I didn't have this overlap problem so much. Here it's not as convincing, so I guess that wasn't like a great demo. But I mean, in general, you're not like going to become some sort of FFT whisperer where you look at the FFT of an image and say, oh, I see what this image looks like, right? So it's not like you're ever going to really visually get anything from it, okay? So as a contrast, let's look at some different images, okay? So, quick question. I deleted them all. Yes?
That FFT function, what was it, BF or BF function?
Oh yeah, the BF one I wrote myself.
Does it wrap the pixels around the edge? Does it intentionally?
So the BF function, right? So if I look at the basis function images, these are the basis functions of the Fourier transform, and they are inherently periodic, right? So they do wrap around the edges themselves, right? Yeah, good question. And just also to let me illustrate what I did make my life a little bit easier by writing this function myself, which is exactly like the tedious stuff that I keep on doing. So I have FFT shift, log, absolute value, FFT. I wrote this thing myself to make it less tedious for me to do it. So from now on, I think I'll just use my FFT instead of cluttering up the screen. Okay, so Now, here is a new image. What was it called? Hut. Okay, so this image has very strong diagonal lines, okay? And so we're going to see that those come out in the FFT. So first I have to make, actually I don't think I have to make it at all. So if I do my FFT of RGB to gray of the hut, what, always put a semicolon. And then I do side by side. So here, again, low frequencies in the middle, but now I see that there are these, diagonal lines here that indicate that there's some activity going on at certain orientations in the image, right? And that comes from these strong diagonal lines in both of these directions here. I'm going to talk on pencil and paper for just a second about why that's true. And in fact, I believe that there is a homework problem where I kind of assigned this as an idea. But you can read off some things from looking at strong diagonal lines. Yeah, question?
So for the FFT, you said it's like if you didn't shift it, you would start from low to high and then go back to low.
That's right.
Then could you be able to just take a quadrant? And is it the same thing?
Yeah, that's a good point. So could you just take a quadrant of the FFT and get what you wanted from symmetry properties?
Right.
Short answer is yes. You don't actually have to view the whole thing because there's always going to be this symmetry. And yeah, so I think that you could think about it like looking at it like a quadrant. That's a good point. To be honest, no one really does that just because it's easier to put the thing in the middle and just see what it looks like. But yes, you could do that, right? And one of the advantages of what we're going to talk about on Monday is a real valued transform that doesn't have these symmetry properties, so you don't have to waste any coefficients looking at symmetry stuff. So there's something called the discrete cosine transform that's kind of like this, but that doesn't have this kind of symmetry thing. Yeah, just like we did for the 1D FFT, you could throw away some chunk of the coefficients and just visualize some of it. I'm not going to talk about it too much here, but we did mention in 1D signal processing that the phase is also something that you shouldn't ignore when you're looking at Fourier transforms, right? And so there's symmetries in the phase too that we didn't talk about here, but well, let's not worry about that right now. But yeah, okay. So let me look at another image that is the closest thing I could find to a high frequency image that was in my Hawaii library here. So if I look at my image, and then this is an image of sand, and now if I look at my FFT of that. So here, one thing to notice is, first of all, this is actually a good example of where, because the image is basically, as edgy throughout the middle of it as it is where it overlaps on the boundaries, I don't get these strong lines coming through the, crosshairs in the middle anymore, because there's not really a big difference between the image wrapping around the boundary. The other thing to notice is that, this middle area is a lot more diffuse than for natural images, right? So if I was to compare this to the valley image, I would see that this image contains a lot more high-frequency information, right? Now, you're rarely going to deal with an image that is like super noisy, unless you're talking about taking an image that you, for example, you guys were working on this burn notice image, right, from the homework 2, right? So, or is it homework 3 that you're doing? Homework 3, okay. So that image, like you could imagine if you had the clear image and you had the crappy broadcast image, if you subtracted those two things, you'd get a very noisy, high-frequency image, right? That's where you might find such a thing in the real world. But in a typical image that you care to take, you're not trying to generate a lot of high-frequency content. But at least you see there's some differences in these FFTs, okay? Okay, so let's go back to notes for a little bit. So again, the bane of Fourier transform lectures is talking about properties. And I'm not going to talk about these in any great detail, other than to say that everything that you know from 1 dimensions carries over to 2 dimensions, and there are some important ideas that kind of correspond to images, right? So one of them is shifting. And so the key idea here is that, just like in 1 dimension, the intuition is that if I shift an image in, if I shift a signal in the time domain, that I'm not fundamentally changing its frequency content, right? I'm not changing the magnitude of the cosines and sines that contribute to it. The only thing I'm changing is the phase of each of those constituents, right? So that means, in image processing terms, that if, if I have an output image, or if I have one image that is like a shifted version, or like a translated version of the input, then my, I guess I need a new, let me just call this G and F for making my Fourier transform notation easier. Then the Fourier transform of this is going to be the Fourier transform of this multiplied by some complex phase shift that depends on the translation. Right? So this here is basically a complex phase shift. And the thing to note is that since this is just a complex number on the unit circle, that the absolute value, the magnitude of the Fourier transform at every frequency is really unchanged, right? And so basically, this just means that, fundamentally, if I translate an image, I don't really fundamentally change anything about its Fourier transform. Okay. And similarly, there are some, natural properties, like if I were to, so basically what I'm doing is I'm going through things that corresponded to the geometric operations we talked about a few lectures ago. If I scale the image, or if I flip the image, I should get the same kinds of things that I expect. So if basically my transformed image is like a scaled version in terms of intensity space of this, then the frequencies are all A times as big as they were before, right? So that kind of shows that scaling the intensities of the image corresponds to scaling the frequency content. That obviously stands to reason because everything is linear. If instead of scaling the intensities, I scale the geometry of the image, if I make it bigger or smaller, so for example, if I have the image undergoing some sort of a transformation like this is like saying it gets, it's magnified or squeezed by a factor of A in this direction and a factor of B in this direction, then I get basically the expected behavior over here. And again, kind of the idea is, suppose that I just say f of 2x, right? That's like saying that the image is twice as small. That means the contribution of the images should be, the contribution of all the cosines should be, mitigated by a factor of squeezing them down by 2, right? Because I don't have the big cosines anymore. Now I have the small cosines. And in particular, if, A or B is equal to -1, then, it basically says that a flip in, a spatial domain corresponds to a flip in the frequency domain. So all this just makes sense in the context of, how should these contributions change as I geometrically transform the image. It all goes according to reason. And another one is rotation, right? So if I rotate the image, so if I say that g of xy is equal to f of xy rotated, let's say counterclockwise by theta degrees, then the Fourier transform is the same as the Fourier transform of the old image, also rotated by the same amount. And that stands to reason, right? Because if I, rotate things, I just should be rotating all the contributions of the cosines. And this is going to be one of the things I ask you to prove on homework 4. And this is just kind of like a simple change of coordinates in UV space. Okay. The key one that we're all familiar with from signal systems is convolution, which is saying that if h of xy is f of xy convolved with g of xy, then in the Fourier transform domain, I have the product of the two Fourier transforms. Now, just a quick comment about this. So here I drew this little, my normal convolution asterisk, but I put a circle around it. And this is important. This is a thing that's called circular convolution. And so I want to talk about that in just a second. But this is the key idea behind making efficient, certainly it was key for time domain convolution, because we would have one signal we wanted to convolve with another signal. We would take those into the Fourier domain, multiply them together. The same thing applies for images. And the reason that we care about this kind of convolution in the image processing world is, again, related to the spatial filtering concept from last lecture, right? Where we take a little bit of mask of pixels and we slide them across. Even though that's more like correlation instead of convolution, we show that it was basically the same thing. And since our filters are often symmetric anyway, it doesn't make that big of a difference. So this is important, although I will say, just as a caveat, that in image processing, most of the time, the filters that we're using for the images are very small compared to the size of the image, right? So, for example, we might have a 1,000 by 1,000 image, and I filter it with a 3 by 3 or 7 by 7 filter, right? And I think it's fair to say that Matlab may not be doing conversion of the frequency domain, multiplication together, and conversion back to apply these very small filters. They may apply them directly in the spatial domain because that may be faster than taking the FFTs of these very small masks. So again, whereas in signals we kind of hit you that for efficiency we always use the Fourier transform to do convolution, I don't think in image processing that's always true, because the image processing filters are often pretty small. So while this is important, or while this is true, it may not have as much functional importance in image processing as it did behind the scenes in signal processing. Okay, but it's good to know. And let me just say again, I feel like I want to remind you of what this circular convolution means. So let me just draw a picture of that for a second. And again, this is really difficult to do on a piece of paper, and if I had some foresight, I would have brought some transparency material, but I didn't. So basically the idea is, again, if I have two signals that I'm doing regular convolution with, so again, I'm going to do this in 1D because it's easier. So if this is my, let's suppose this is one signal, okay? I'm just going to mark off some numbers here. So let's say this is my signal 1. And let's suppose I want to convolve that with signal 2, which looks like this. Right, the way I do that is I flip one of the signals over and I drag it across this other signal, and I plot the integral of this against the dragged signal at every instant to show the picture of the result, right? So what I would do, for example, I'd say, if I were to flip this at some point, this is like my g of some offset minus x. I would look and see how much overlap there is, and then I would make a plot of that overlap as time goes on, right? So in the beginning, I get nothing. Here, in this case, as I bring this along, at some point I reach the most overlap, which is going to be 200. This box is going to stay inside this box for 100 units. And then after it moves off the end, it's going to slowly tail down like this. Right? So this is kind of like a sophomore level convolution problem, right? So, like I just told you with those real images, though, in the discrete world, we're assuming that everything kind of overlaps periodically, okay? And so circular convolution basically means that instead of these images, if I thought about these as 400 by 400 images in some sense, right, the implicit convolution process, circular convolution process in Matlab is going to be saying, okay, actually, the way that we would be thinking about it as a circular convolution would be like saying, okay, if I were to draw this picture again, I'd have this, but the implication would be that this thing would be repeating this would be like periodically extended. Same thing with G. So if I were to make a picture of that, now if I were to flip this around, this is going to be a little hard to draw, but basically what I would have instead would be something like this, where, now let's see if I get this wrong. So it's going to look something like this. Right, as I flip it and drag it across, that means that, there are certain places. So for example, if I were to drag it across like this, where this is just over the line, like this, that would mean that I have to look at not only this integral here, but also it's possible that there's some stuff from the periodic copy that's hitting this guy, right? So if I were to look at my periodic convolution, what I would get would be something where actually there would never be any zero values. My circular convolution here would look something like this, as it would turn out. And this is kind of an exercise to do at home. It would look like this. So again, the idea here is that this is going to be a periodically extended thing itself. Oops, crap. So basically, F circularly convolved with G is a periodic signal itself. And the problem is that this may not be what you want. Since copies may intrude into regions we don't want or we don't expect. And so the solution to this problem, which we talked about in DSP, is that if I were to take these signals and I were to extend them far enough, so instead of imagining that the period of the signal is 400, if I imagined it was something like 700 instead, then when I flip the copies around, I would never have any extra overlap that would cause me any problems. And so the solution to these problems is zero padding signals so that copies don't unexpectedly overlap. And so again, this is really an issue if you are implementing like your own convolution algorithm, your own FFT algorithm in Matlab or in a circuit. You have to be aware of this issue. Yeah, question?
Why does the circular convolution not start at 0?
Why does it not start at 0? So let's look at this example, right? So here, why does it not start at 0? Well, the 0 position of this convolution would be like this. Right? And then I would see that there would be this 100-sized overlap between the right edge of this guy and the left edge of this copy.
So you push it to the negative as well?
Yeah.
Okay.
And so if I wanted to avoid that problem, what I could do instead would be, in that case, what I could do is say I could zero pad, say to length 600, which is going to be overkill, but we can at least see how it looks. So that would mean that here I would have a picture that looks like this, 400, 500, 600. and I would zero pad my other signal to be like this. Then, when I flip this guy around, my copy is going to look like this, and then I'm going to have, this is going to be like my f of x, this is going to be like my g of x, this is going to be my g of minus x. Here, now there's no danger, right? Because if I compare this guy to this copy doesn't intrude on that, right? And when I looked at my convolution, I would get exactly the thing that I expect I would get without any sort of corruption, right? Here you can see that actually I could get down to basically, how far could I go? Basically what I would need would be that this edge here could go down to like 301 before I'd be worried about there being some sort of overlap. So really I could have gotten away with zero padding this to 300 plus 200, like basically 500 or 499, something like that, right? So actually I think that I have it written down. So, zero padding to at least dimensions M1 plus M2 minus 1 by, so these are basically the dimensions of the images. Right, so basically have to add some zeros to the ends of those images to make sure that there's no overlap when I flip one around, right? And, that's sufficient, but I mean, again, we talked about efficient FFT algorithms, and you could imagine that if I wanted to be truly efficient, I could zero pad up to the next power of 2, for example, that was above this number for efficient DFTs, right? So, I don't have to screw around with some odd number DFT. I could just make the most efficient DFT I want to above a certain value. So the good news is that Matlab does all this stuff for you. So you really should never have to worry about this yourself. So for example, the filter2 command that we talked about last time, and I believe also the imfilter in Matlab, does all this for you. So basically, it will figure out, okay, so I need to zero pad the signals to this thing, I need to do my circular convolution, and then I need to crop down to the image that the user wants at the very end, right? So, in modern life, where you guys are living, you really don't have to worry about this stuff yourself unless you are asked by your boss to code this onto some sort of processor that doesn't have a built-in FFT on it, then you may have to be aware. Question?
The circular padding corresponds to the size of the filter, right? Not the size of the image itself.
Right. So I mean, it involves both in some sense, right? So basically, if I look back at how much I have to pad, right? So if this image size is fixed, and this is a, say 3x3 filter, this tells me that I have to pad the image by, 2 in each direction to make sure that the filter doesn't, screw anything up, right? It would be a bigger issue if I was, for some reason, convolving like 2 large images together, and I'm not sure why I would want to do that. We'll talk a little bit about one reason why you might want to do that after the exam. So for example, correlation, running a template across an image to find an object is something that may work for some applications. And if that object mask is big enough, you may need to kind of keep that in mind when you're doing your filtering. But I wouldn't worry over much about it. The other thing that I wanted to mention just real quick is, as a side note, okay, so before I move on, so any questions about that? I know, tedious, but important for down the road, just in case you already need to know it. Okay, so another final comment is that we saw in that example with the hut that if I have a strong image edge in one orientation, that manifests itself as something very visible in the DFT. And so I want to just kind of say why is that true. So here's kind of a note or a theorem. So if an image has strong image edges at theta degrees, we see a strong contribution in the DFT, the 2D DFT, at theta plus 90 degrees. Why is that? So let me just do an example of that. So here is a little Matlab script I wrote. So what you're going to see is here is an image on the left, right? And here it's its DFT on the right. So I have these strong vertical bars, and in the Fourier transform I see a strong horizontal bar. So why is that? And as I rotate these bars, here, basically I'm rotating these a little bit to the left, and the contribution in the Fourier transform seems like it's 90 degrees offset from what I might expect. And as I rotate it around, I continue to see the same kind of phenomena. It's not perfect because of, the bars are sampled, and so that means there's some weirdness in the DFT. But you see the basic idea that why is the bar going the other way? So we can just kind of show conceptually why that's true. Oops, sorry. Okay. So let's think about, this image here. So this is kind of like the first image I showed, where I have some strong bars. So let's imagine that this is my x direction, this is my y direction. And what I see, what we kind of saw in that Matlab example, is that if this is the u direction and this is the v direction, I saw something that looked kind of like a bright bar here and dark here, right? Well, this actually kind of makes sense. So one way to think about this is that, how do I generate this image, right? So this image is kind of like saying I take a vector of constant values and I outer product it with a vector of stripes. Or I guess if I was being, careful, this would be like vectors of multiple, so maybe I have a bunch of white and then a few black and a bunch of white, right? But basically, this is some function here. And so now, again, since the DFT is separable, I can think about what would I get if I took the DFT of both of these things? Well, so the DFT of a constant is a delta function, right? Which means that the DFT on this guy is going to look like basically, if I put the DC in the middle, it's going to look like this, right? And the DFT of this guy is going to be whatever it turns out to be. So for example, if this is something that is high frequency, it's going to look like, if I put DC in the middle, again, there's going to be, nothing at DC, and then there's going to be some high frequency stuff at the high frequency part. And then when I outer product those things, what I'm going to get is zeros above, zeros below, and then I'm going to have something that depends on the periodicity, the frequency of this thing over here, right? So I can kind of see that even though things are oriented this way for the stripes, I'm going to get a result that is, oriented this way in the DFT. And so that kind of just pops out of the fact that the DFT is separable, right? And the result follows by saying, okay, I stated before that since if I rotate the image by theta degrees, I also rotate the Fourier transform by theta degrees. So that means that if I rotate this guy a little bit, then I rotate that guy a little bit, right? So this is a very hand-wavy argument to show why you get angles in the FFT or the DFT that are maybe not what you would expect. I'm not sure if I had prepared better. not sure whether I have no. This may be one of those. Looking for an old image of mine. I guess I may not actually have it here. Well, we can try it. I thought I had a Sudoku image. There you go. So here is an example of an image that has strong rows and strong bars in the rows and columns of the Sudoku grid. And then if I do my FFT of that image, and then I put these side by side. So again, this may not be the greatest example, but basically, some of these guys, like I think that what's happening is that these bars here are generating this stripe, and the up and down bars are generating this stripe, right? So if I were to actually match these things, and the problem that's confusing here is that since there are two, this is a crappy example, since there are two right-angle grids, it's hard to disambiguate the fact that this bar here is actually not corresponding to the strong, almost horizontal bars. It's corresponding to the other one. So it would be a good example of well, I guess the Matlab example I showed you is the one I wanted to. But anyway, you can kind of see that you just want to be careful, right? So if you're trying to interpret this image, you want to make sure you know what you're looking at. That example probably confused you more than it did enlighten you, but anyway, we all learned something. Okay, so any questions or comments? All right, so what I want to focus on next time is basically functionally using the Fourier domain for filtering, right? So we didn't actually filter any images yet. We just kind of showed what their FFTs look like. And so what I wanted to show next time is talking about some of the ways that the spatial filters we talked about in the last lecture, how they look in the Fourier domain, and then how the Fourier domain helps us filter images. That part is not going to take us very long because it's pretty straightforward. And then I also want to talk a little bit about, we talked a lot about aliasing and sampling in one-dimensional signal processing, right? We had Nyquist theorem and all this stuff. And so I want to talk a few words about what is aliasing and sampling, how does that manifest itself in the image domain. All right.